John Kovac from Harvard University, and he's going to tell us about B modes from the ground.
Thank you. And thank you for having me. It's a great pleasure to be here. This talk's going to be a change of pace. This is going to be a very much an experimental focused talk focusing on the challenges and prospects for measuring R using ground-based telescopes. So these are now the L of 100 B modes that Joe was talking about, the smaller angular scales. And it's a particular pleasure to be here in this venue because 11 years ago at Cosmo 2002, an experiment dear to my heart, this is my thesis experiment actually, first detected the polarization of the CMB and announced at this conference that detection. And there's the map that was made, and a lot of the same features that identify this work, this survey, actually apply to the experimental challenges that are now being faced by the current generation of telescopes. So this map was produced on a very limited patch of the sky. It's about 3 by 3 degrees, and the E-mode polarization that was measured has an RMS of about 3 microkelvin on that field, and it was measured with high signal noise, actually a signal noise peaking at 3 on scales of about ½ a degree in that map. And that was an initial detection. It was big news. We were very happy. So now B modes from the ground. So even when we made that initial detection, theoretically it was a bit of a yawn. The E mode polarization looked exactly like the theory predicted it to be, and everyone was oriented already from the start towards the prospects of uncovering new physics in the B mode polarization of the CMB, and we knew that we had a long way to go. So B modes from the ground, what are the features of the experiments that are going after this from the ground that are in common? Well, ground-based experiments can achieve deep concentrated coverage, unlike a satellite where you tend to cover the whole sky. And that means that your primary strategy on foregrounds is avoidance. You're also limited in your frequency coverage when you're on the ground to 2 or 3 bands where you can get good sensitivity, 4 at most. And so you use the limited frequencies, but picking the cleanest patches of sky. Systematic control with repeated in situ calibrations. You can access your telescope. You can make very precise measurements of it in the field while it's observing. Large detector count and a rapid technology cycle. So when you have your telescope on the ground, you can go every year. You can update it with the latest focal plane technology. And so experiments on the ground have seen this very rapid turnover in their sensitivity from year to year. And relentless observing. So when you're concentrating all your coverage on a small patch of sky with a large number of detectors, you're scanning that patch sometimes multiple times per day. This yields many, many redundancies in the surveys that you accumulate. And so there are a large number of consistency tests that can be formed with these data sets. So all of this, in my opinion, gives us a powerful recipe that's optimized for high confidence initial discovery. So it's definitely not the best for doing comprehensive cosmology, but for targeted science, these ground-based surveys are excellent, and particularly for this application of going after R. I think ground-based surveys will find a niche here. So, so how have we done in the last 11 years? Well, I said we had a long way to go, and it's true the E-mode polarization spectrum has now been measured by many experiments to relatively high precision. You can see it's nothing like the precision of the temperature spectrum measurements now, but we're eagerly awaiting the Planck data and the new generation of polarization experiments that are going to have of order 1,000 detectors from the ground are going to add a lot to this E temperature spectrum measurement. B polarization, the direct BB autospectra measurements are still only upper limits, and that remains true now. So the best upper limits here are provided by BICEP and at the smaller angular scales, the quad experiments. There are some other experiments here providing competitive upper limits from Atacama, the quiet experiment. But still seemingly a long way away from this goal of detecting the tensor bump at L of 50 to 100 here in the B modes. That line is shown for R of 0.1, which is the maximum signal compatible with the current Planck data. And so the previous generation telescopes still have quite a ways to go. That benchmark there is 100 nanokelvin that they can aim for. It's a very faint signal. Okay, but progress is being made rapidly, and Joe showed this, this detection beautifully, so I don't have to say very much about how SPT used an external data set, mapping out the lensing potential, and used that in combination with their E-mode polarization measurements to predict the form of the B-mode signal in their data. And then in a cross-spectrum analysis, which, as we all know, is easier and cleaner with respect to systematics than doing an auto-spectrum analysis with your data. So when you can use an external data set to predict the form of the signal and the modes you're looking for, it gives you a great way to do a simple analysis. And SPT beautifully pulled out the predicted B-mode lensing spectrum. And this came out just last month. So that's really encouraging. We can expect a lot more from these polarization experiments on the smaller angular scales now that they've scaled up to this huge number of detectors count. So let's see. To show you where some of these ground-based telescopes actually operate, many of them are at the South Pole. It's a nice place to be a CMB telescope. You get to live in a beautiful observatory building here. Not shown on the bottom part of this figure here is because the photo's being taken from the main station, are the facilities where you eat and you work. So it's a convenient place to work. You can see the transportation's provided. And the scale of the experiments here is very impressive. This is the 10-meter South Pole telescope. And the Bicep 1, Bicep 2, Bicep 3, and Keck ray experiments that I'm going to be talking more about, really targeting this degree scale polarization. Atacama CMB telescopes. This photo is probably a couple of years old, but ACTPol and ABS are operating here on this site, and Polar Bear has just set up shop there. I can zoom in and see what that neighborhood looks like. So you can see also a very large scale of operations set up there in Chile. Okay, so to hit a few of those points on common features of ground-based CMB B-mode searches. So galactic foreground avoidance. So you want to go where the foregrounds aren't, obviously. And this was the picture when we first chose our observing field in the middle of the last decade, using the best information, which at that time on synchrotron polarized foregrounds was coming from the WMAP polarization. And we could use that to predict the low frequency end of the polarized foregrounds here. And at the high frequency end, the dust polarization. So here, just a very simplistic model, taking an FDS unpolarized dust model and multiplying it by a 5% polarization fraction at high galactic latitudes gives predictions that look like this. You can see there's a lot more contrast in the dust than there is in the radio emission at high galactic latitudes. And that pushes you up to higher frequencies, somewhere between 100 and 150 gigahertz, as the sweet spot if you're going to pick the cleanest region of sky to do your work. That's what we and many other experiments now have done, is to pick a region like this, the southern hole, where you concentrate most of your observing time. That red box is 2% of the sky. Okay, so I touched on systematics, and I'm going to talk more about it in some detail in this talk, but just to frame the challenge here of one kind of systematic, one that we spend a lot of time worrying about, that is the leakage into the polarization signal of your experiment of much brighter unpolarized temperature signals here. Okay, so let's start with the goal here. The typical degree scale brightness fluctuations at 150 gigahertz, if we hope to measure B modes at R of 0.01, those are 30 nanokelvin signals. Okay, so the lensing B modes, which are not at degree scales, they're at arc-minute scales, are 10 times brighter at 300 nanokelvin. The CMB primary temperature anisotropies, which of course are all over the sky, you can't get away from them, so even if you pick the cleanest region and you have perfect shielding, they will be in your field of view, are 1,000 times brighter. And so you have to have exquisite control of your experiment to be able to reject the temperature signal and measure polarization at that level. Outside your field, hopefully, is the galaxy, and typical brightness fluctuations there at 150 gigahertz might range from a few tenths to 30 millikelvin. So here now we're talking 10 to the 4, 10 to the 6 times the science target. So you have to have excellent side lobe control onto the galaxy. And the atmosphere and the ground will contribute brightness fluctuations on these degree scales that can range from tens of millikelvin up to Kelvin, depending on which way you're cutting across the atmosphere. And the ground, of course, in the worst case scenario, you can measure gradients of up to 300 Kelvin. So this is quite daunting, and I was encouraged by the speaker yesterday who, I hope I got the quote right, he mentioned with respect to direct dark matter searches, the backgrounds are horrible, but people are brave. So I hope we are. We've taken on the challenge anyway. Okay, so I'm going to talk in some detail about this particular experimental program, the BICEP and Keck array series of telescopes, because we're in the field, we've got quite a lot of data, we're a little bit ahead at this stage, but there are many other experiments that are now taking data and operating, and I think that the experience that we have is going to be somewhat illustrative of the results that you can expect to see in the next year or two from all of these groups. So starting with the BICEP 1 generation, and you see the timeline up here, 2006 to 2008. Okay, so Team BICEP was a relatively small team. These experiments have all scaled up to some extent, but this shows us with this small BICEP telescope before we shipped from Caltech at that time, with Andrew Lang as our PI. And so why use such a small aperture for your CMB telescope? Obviously, you're giving up information on the arc-minute scales, where there's a lot of cosmology to be done with the polarization. For a targeted experiment, a small aperture is very efficient to integrate, to test, and to deploy, as you can see here. And it also means that you can put the entire telescope in the cryostat. And so your telescope can be at 4 Kelvin. You get great stability of the telescope and the beams. Your aperture being small can be completely filled with calibrators. Your far field is not very distant. You can access it experimentally very easily and very directly with no reimaging optics or anything else. You simply put a source 200 meters away and you're comfortably in the far field with a telescope like this. And so you can do very precise beam maps easily. A small aperture allows you to rotate the entire instrument. So you can have a mount that has a third axis of rotation, which is impractical if you've got a 6 or a 10-meter telescope. And so that gives you a lot of systematic control when you're designing a polarization experiment. And a small aperture allows you to achieve superior side lobe suppression, of course. Okay, so I can't resist showing you a little bit about what it looks like to work at the South Pole. Compared to sighting a 10-meter telescope there, which happened the next year, this lift was pretty easy for the guys down there at the South Pole. They just picked up our little telescope with their crane. We cut a hole in the roof, and they dropped it through the DSL observatory. Here's the inside of the observatory and putting the instrument together. So this is the BICEP 1 receiver, and you can see this forest of feed horns here up on top of the receiver. Behind each one of those feed horns is a PSB pair that's very much like the polarization-sensitive detectors on the Planck satellite, except BICEP has of order 100 of these detectors, as opposed to the few dozen that are flying on Planck. So this is the sub-Kelvin refrigerator. The 4 Kelvin telescope tube goes on top of that, and the entire thing goes into a liquid helium cryostat. That helium cryostat in turn mounts onto this telescope mount, which pokes up through that hole in the roof and forms a nice convenient observatory. So almost immediately we got to work characterizing the instrument, its polarization response and its beams, and we've been doing that nonstop ever since, with every season refining our procedures. So what I'm showing here is actually several generations in calibration measurements, now with BICEP 2. Precision beam mapping on site. We've got a precise flat mirror that redirects the beam of the telescope over the rim of our ground shield towards a source that's on a mast over here that allows us to form precise beam maps on unpolarized sources and we can put a rotating polarized source up there with known orientation, and we can measure the response to a polarized source, getting the polarization efficiency and angle very precisely in the far-field beam. So you can see the response to an unpolarized source when we difference two oppositely polarized detectors, vertical and horizontal polarized, as we would for making a polarization measurement on the sky. Doesn't look that hot, and that's actually true for BICEP 2's beams. There is a significant amount of pointing mismatch between two coincident detectors in a pixel pair, 2 arc minutes, which is a decent fraction of the beam size, 30 arc minutes. And so that's something that we account for in the analysis. We have excellent knowledge of, and I'll talk a little bit more about that coming up. That's one of our large experimental challenges. So aside from just that main beam mismatch, it's important to map the entire beam response. So that ratio between the temperature anisotropies and the polarization signal that we're after of 10 to the 3 sets a scale for how well you need to understand all of the integrated power in your beam. You can't tolerate missing solid angle at that level of 10 to the 3. And so we have worked very hard to form beam maps that are precise on a detector-by-detector basis. Here you see a number of single maps taken at different instrument orientations, all of them composited after cross-checking for their consistency into this map here, and 4 orders of magnitude in the depth. You can see the main beam here. You can see the first airy ring of that and some asymmetry in that, which is very interesting. You can also see a crosstalk beam here that's at the 3 or 4/10% level. And that's also something that needs to be accounted for in an analysis like this, but we measure it precisely, and this is a systematic that we understand quite well. The crosstalk comes from our squid multiplexing system. All right, so just more on precision beam mapping here. You can see now taking a radio profile and integrating, you can see the first, second, third, fourth, fifth airy ring, high precision in this data. In profile, the data is here. The blue is a physical optics model. You can see they don't agree precisely, and you can also see there are significant differences between the two polarizations. All of this is something that you care deeply about if you're trying to measure signals at 30 nanokelvin. Side lobe characterization. Now, far side lobes, we can, with our small aperture very easily, when we get our graduate students out of it, mount a blackened baffle on the front of our telescope that can intercept all of the far side lobe power very effectively. You can put your telescope in an absorbing microwave bucket. So a small refractor gives you an unobstructed aperture, allows you to use that black 4 baffle, relatively small reflective ground shield. The combination of those things gives us response with the 4 baffle at angles that are outside our main field of view, 30 degrees away, at the minus 40 dBi level, or if you'd like, 9 orders of magnitude from the main beam peak response. Okay, so some sky coverage with BICEP 1. We spend most of our time observing this clean southern hole region. We spend a small fraction on the galaxy. You can see that drifting past in this wonderful movie made by Cynthia Chang. In the 3 years that BICEP 1 observed, we collected over 10,000 hours on our CMB target field. So that is comparatively good observing efficiency. Of the 25-odd thousand hours that we might have had in those 3 calendar years, 10,000 of them were actually spent on our CMB target. For a ground-based experiment, that's excellent. Obviously, for a satellite, you do much better. E modes and B modes published to date. Okay, so here are those E spectra again, and now highlighting the published results from the BICEP 1 telescope. These limits here on the B spectrum place a limit on R at the 0.72 level, 95% confidence, and that came out in 2010. Since then, we've been working on fielding new telescopes, but we've also updated the BICEP 1 analysis to include more data, the third year of observations, and we introduced additional channels. We've spent a lot of time getting our statistics polished and just right. So 52% more data, better noise modeling, better likelihood estimation, better control of systematics developed in one sense in particular. So this is a deep projection of certain kinds of temperature to polarization leakage come from main beam mismatch, where we take our main beam and we Taylor expand it up to second order here. So this is the main beam response to a temperature signal. And if you have a pointing mismatch, it's a combination of these first two terms, the first derivatives. If you have a beam size mismatch between your two polarized detectors, it looks like this. And if you have differential ellipticity, it's these combinations of the second derivatives. So if you have a precise map of the temperature sky, which WMAP and now Planck have given us, you can take these modes and you can form a template for the potentially contaminated modes in your time stream data. And that's precisely what we do, detector by detector. And we deproject those modes. We actually just identify those modes and we set them to 0. It's equivalent to marginalizing over them, or if you'd like, to fitting and subtracting. It's different from saying that we're going to measure the mismatch precisely enough to correct for those modes and subtract it off and recover the information from those modes in the data. But it turns out we could do either because we have very precise measurements of our beam mismatch. OK, so for the BICEP 1 3-year analysis, we applied that deprojection technique just to the dominant systematic uncertainty at the level of the BICEP 1 sensitivity. That was the relative gain uncertainty, so just the first of these modes here, this one, between the two detectors in every pair. So we believe that we had characterized those, and it was producing a maximum false equivalent R signal at the 0.15 level. And so by deprojecting that mode out of our data, we've eliminated that potential systematic. But more importantly, we've developed this procedure for use in our future experiments. OK, so the BICEP 3-year polarization maps, now displayed as E-mode maps and B-mode maps, are shown here on the left. The E-mode map obviously has more signal than the B-mode map. The B-mode map is consistent with simulations of pure noise. So I mentioned null tests. Here is one, the so-called deck orientation null test, where you take the telescope when it's been pointing in certain orientations, and when it's rotated around the bore site to a complementary set of rotations, and you subtract off the signal, the cosmological signal, and you're left with something that should be consistent with noise and with any systematics that have been thrown into relief by that subtraction process. It's a powerful null test. It's one of 7 or 8 null tests that we rely on for the BICEP 1 analysis, and it confirms that the map noise is integrating down. In the case of the 150 gigahertz BICEP 3-year data, we're at this level of 500 nanokelvin in square degree pixels. And how far does that get us on the B spectrum? Well, here's the E spectrum, measured with high signal to noise, and the B spectrum is shown in black. And here, again, the B spectrum blown up with the 2-year result and the 3-year result showing very good consistency. We actually wound up with a relatively unlucky draw, adding in another year's worth of data. The result did not improve by that much. The upper limit on R is at the 0.70 level now at 95% confidence, and R is 0.06, plus or minus around 0.25. And it's just a little bit above the median from SIMS, but very consistent with the simulated universe here in which R equals 0. OK, so the initial results that we and the rest of the field got back from BICEP 1 is that there's a green light. This is essentially doable. It is possible to make a high signal noise measurement of the CMB polarization at L of 100 and to do that from the ground. The instrument worked as designed. And systematics seem controllable, we believe, all the way down to R of 0.01. So we were encouraged by this. Many other people were encouraged by this and built slightly different experiments as follow-ons to this. Also, this is hard. 3 years of data have yielded a result that still is not anywhere close to touching the indirect limits that are being produced on R by Planck. At R of 0.07, we obviously need a lot more sensitivity if we want to push into that interesting regime of R of 0.1 and below. So more sensitivity is exactly what the field is all about right now. So BICEP 2 and the Keck array are shown here. And in these cartoons on the bottom, you see how the detector count is increased from the BICEP 1 focal plane to BICEP 2 and the Keck array. So let me see. I can show this in more detail. All the current generation experiments now use mass-produced superconducting detector arrays in their focal planes. So this is our focal plane. Here is a silicon tile blown up. It is an array of 64 pairs of polarization-sensitive detectors. In this case, they're formed by arrays of slot antennas. You saw SPT poles horn-fed array, but again, monolithic wafers form the detectors behind that horn array. These slot antennas, the vertical and horizontal slots, are feeding a pair of detectors associated with each pixel, and those detectors are transition edge superconducting bolometers. And here they are, operating at around 250 millikelvin. Talked about the rapid development cycle with these experiments, and BICEP 2's focal plane was deployed to South Pole only in January 2010 for first light later that month, and observations starting that February. We actually constructed a clean room at South Pole for this, and SPT uses that same clean room, and every year we upgrade our focal planes down there on site, and other groups do the same now. So that's part of what is fueling the rapid advances in sensitivity with all the experiments operating in the field. So the Keck array, what is that? Well, it's essentially 5 BICEP 2s. So rather than using liquid helium, which is difficult to supply in quantity at South Pole, we switched to pulse tube coolers now, and we've made a compact version of this cryostat. We could fit 5 of them into the old Daisy mount. And this gives us a total of 2,500 detectors on the sky right now. Okay, so I'm actually going to show you a little raw data. I'm not going to apologize for this. This is an hour's worth of data from our telescope, 500 detectors, time streams overplotted, and you can see the mount motion is up here on the top. This is time running this way, and we start and end each hour with a little elevation nod, a mini sky dip that excites all of the detectors on the gradient of the atmosphere. This is relatively good weather, and the atmospheric signal in the detectors looks very clean. The detectors that are higher in the focal plane respond less than the detectors that are lower because their air mass is being modulated less. Otherwise, they look exactly the same. So this is the pair sum, or the temperature data. If you take 2 detectors that are in a pair and you add them together, and if you difference them, you get the polarization signal here. You can see in this weather, the pair sum looks only slightly noisier than the pair difference. The weather gets a little bit worse, and you start to pick up tens of millikelvin structure across the atmosphere as you're scanning back and forth, but you see at that level the atmosphere is largely unpolarized. And so this is the data that we typically process. We have 3 years of that data with BICEP 2 in the can right now, so 17,000 scan sets, which is what I just showed you, approximately an hour's worth of data, now under analysis from BICEP 2 from those 3 years. 18 terabytes of data, and there's a lot of sophisticated pipeline coding machinery that goes with processing this volume of data. So I've got to call out Clem Preich, who's responsible for overseeing our efforts and our team on this coding effort, and produce some of the plots on the next slides. Okay, so cumulative weights of BICEP 2, you can see that the weight, that is the variance, the noise in the data, or the inverse variance, I should say, has increased steadily as we got better at tuning up the detectors through the course of these 3 years. We had an opportunity to do that because we've got an experiment that you can poke at and continue to optimize. And so you can see the last year of observing acquired almost half of the weight, the total weight of the 3 seasons. And BICEP 2's 3-year maps look like this. So now the Q and the U Stokes parameters on the sky are reflecting primarily, you see this grid-like pattern here that's vertical and horizontal in Q. That's the E-mode structure in the sky bleeding through into Q and coming in again at plus or minus 45 degrees in the U maps. So BICEP 2 has achieved a sensitivity of around 120 nanokelvin in degree pixels. So in Keck, in its first year operating with 5 receivers, didn't quite equal that, 170 nanokelvin. In its second year operating right now, it's now surpassed this. So together, 2 seasons of Keck have just acquired below 100 nanokelvin in degree pixels sensitivity on the sky, which is quite a milestone. But we're focused right now on the analysis of the BICEP 2 maps. Okay, so how do we analyze those maps? Well, in a nutshell, you take their Fourier transform and then you square. And if you bin up in annular bins, you can see now that these axes, both of them, are read in L. So the annular bins here are the angular power spectra, except we've got Fourier transforms of the Q map and the U map. You can see missing along the vertical axis are some modes that have been filtered out by our scan strategy. So you can take these Q maps and U maps and locally transform them in the Fourier planes, very simple to do, into E and B. And if you rotate them into E, you get something that looks like this. Okay, so this is the E mode power spectrum in 2D, directly read from our map. You can see the first peak here in these annuli around L of 100, L of 120, and the second peak here in annuli that are out around L of 300. So we just bin up around these annuli to form our power spectra. Null tests that we perform, well, it's a very simple illustration, of course, is if you bin up the first half and the second half of your data and you subtract. And it looks gratifyingly clean on the same color scale. Of course, we do a much more rigorous test than that, but I wanted to show you that you can construct systematics tests that throws certain instrumental effects into stark relief. And so if we perform a deck null test, again, rotating instrumental orientation and forming a difference, we can get it to fail quite easily. And the reason is that this data set has a large degree of this kind of mismatch between the beams. So this null test differences subsets in the map that maximize the non-cancellation of the dipole form of the temperature to polarization leakage. However, deep projection can remove this very easily, and so we deep project all of these modes, and the net result is that it cleans up. In fact, it winds up being quite consistent with signal plus noise simulations after that process. We perform this deep projection on every detector pair at the time stream level, and we allow the coefficients to vary with time, although we probably don't have to. Okay, simulations. So we do full time stream simulations, and that's the basis of our analysis. All the E to B mixing effects are included in those simulations, whether from map projection, sky cut, filtering, the deep projection operations, and the E to B mixing is debiased using those sims. We find that using heuristic pure B estimators, like those invented by Kendrick Smith in 2007, is a useful estimator for us for B, for eliminating the variance from cut sky-induced E to B mixing. So that certainly helps a bit, works well down to R of 0.05. We've got improved estimators that are under development to reduce that E to B mixing and take us down to lower levels of R without suffering a penalty from the E power that's being leaked into B. But we can remove that, we can predict that very precisely and remove the bias in our data set. So systematics are being extensively probed. We've got of order 14 now of the most useful combinations of null tests. All of those must pass. We also do extensive forward simulations using each measured systematic, including now the full beam model that I showed you some of on previous slides. That allows us to characterize what level the undeprojected residual temperature polarization leakage is in these data sets in detail. Okay, so now I'm going to show you, this is not real data, these are simulations, but this is an output of simulated signal and noise B modes from lambda CDM and R equals 0 in this simulation. So this is a simulation derived from the bicep 2 level of noise, and I'm going to add in R of 0.1. So in principle, that is the level of sensitivity that our experiment is at right now. And we're working very hard on this analysis, you can imagine. Okay, so I will show you the real data's E mode map here and its B mode map. And the name of the game is what is this map consistent with? Okay, so the race for R. It may seem like this has been a long time coming, 11 years. But progress has actually been much faster than it was expected. So the CMB task force report, for example, which came out shortly after polarization was initially detected, charted a course for measuring R that had us reaching these levels of 100 nanokelvin in degree pixels sometime around 2017. And that's what we've just achieved in those maps that I showed you. We're going well. It's driven largely by the development of these very large format focal plane arrays and the rapid deployment of those into the field by us and by many other groups. And some of those other groups I should mention now. Bicep 2 and Keck-array, starting with the small aperture experiments and working towards the large aperture experiments. Small aperture experiments here being optimized really for these degree scale B modes. Bicep 2 and the Keck-array of order 500 detectors and 2,500 detectors. ABS, which has been taking data in Chile, has 480. EBEX, balloon, which flew last year from Antarctica with 1,200 detectors. The Polar Bear telescope, operating from Chile, 1,200 detectors since last year. ACT-POL just came online last month with, I believe, 1,000 detectors initially, working up to 3,000. And SPT-POL, 1,500 detectors since last year. Coming in 2014, SPIDER, another balloon. Bicep 3 will add another 2,500 detectors at the South Pole. And then beyond that, probably in 2015 or 2016, we have another balloon, Piper, and upgrades to SPT, Polar Bear, and ACT-POL are all planned with over 10,000 detectors now. So that is where the field is going. The scale-up has already happened to class 1,000 detector experiments. And we can expect results from multiple groups with complementary systematics and in many cases, overlapping coverage. So we put together this plot showing experimental progress where the raw aggregated experimental sensitivity now is shown here as a function of year for some representative experiments. You see the Planck satellite, the current generation of ground-based telescopes, have equaled Planck in sensitivity, but we're concentrating it on a very small patch of sky. These are the class 10,000 generation of experiments, class 10,000 detector generation of experiments that are going to be operating in the coming couple of years. And then what we've been calling stage 4, CMB-S4, class 100,000 detectors is shown here. And this is something where the CMB community has tried to organize and reach a consensus on what we think is achievable if we work together for what happens next after the stage 3 class 10,000 detector experiments. From the ground with 100,000 to maybe even as many as 500,000 detectors on multiple platforms spread across multiple sites. So that is the CMB-S4 experiment as it's been spec'd. So I'll get back to that in one slide. B modes from the ground. Okay, so I've already run through this bullet list, and hopefully I've convinced you how these pertain to our experiment. I think that they are general features that we can expect. How deep can we go on R? So I think that we can hope that the current generation class 10,000 experiments can push down to this regime R of 0.01 in the next several years. We hope to get there by the 2015-2016 timescale. And then going further than that will require pushing even on the best 1% of the sky deep into the foregrounds, both the galactic foregrounds here. These lines now come from the Planck sky model. And of course, we'll have more information on those foregrounds shortly. And deep into the lensing signal by applying de-lensing, that is measuring the lensing potential using the information out here and undoing the lensing on the degree scale B modes here to dig down, in both cases, by a factor of 5 to 10 in map space to reach this level of R of 0.001 for a 1 sigma sensitivity on R. It's going to be a tall order, but the consensus of experimentalists in the field in the US, at least this summer, was that we think that we can spec such an experiment, and we're excited about working towards it. Pushing below this R of 0.01 threshold, of course, takes us past the boundary between large field and small field models of inflation. And we heard yesterday about the Starobinsky effective potential here at R of 0.003 or so, and think that that is probably in reach with the CMB-S4 experiment from the ground in the next decade. So these different lines here are projecting different sensitivities for different scenarios of how deep we can go in the foreground removal and what degree of de-lensing we can benefit from using different size apertures, different resolution on the CMB lensing signal. And all of these scenarios can achieve less than R of 0.001, 1 sigma uncertainty on R. So that's the end of my talk. I just want to convince you that there are a lot of experiments taking data right now, including ours, and the next year will be exciting. with the results we can expect to see from this generation of experiments. I expect that Planck will have something to say about this plot in the coming year, and I think that many ground-based experiments will as well, so watch this space.
Well, thanks very much for a fascinating overview of the future of tensor modes. One quick question. Yeah.
Hi, just a comment about your two slides before. Yeah, that's the one.
Yeah,
The one after this.
this one.
Yeah, so just a comment that you don't really require large field values to get large tensor to scalar ratio. In principle, you can get roughly of 0.1 even with small field values. So delta phi can be less than 10 times. You still can get large R.
Okay. Just a comment. All right. Just before we go to tea, which is a bit late, I apologize for letting George go on for so long. Just remember that if you're giving a parallel session this afternoon, make sure you put your talk on a memory stick at the registration desk. And remember, there are two directions for getting coffee, okay? Left or right. Go the line of least resistance. So let's thank our speaker again.